Alright guys, let's see if we can solve question 12 from the chapter 8 of Beer&Johnston textbook. And in this one we have a 20-pound block A and 30-pound block B that are supported by an incline that is held in the position shown. We know that the coefficient of static friction is 0.15 between all surfaces. So the surfaces that we have in here is the surface between A and B and the surface between B and the incline. And we need to determine the value of the theta for which a motion is impending. So we are looking for this theta in here when the motion is about to happen. So we are technically in equilibrium and we are like 1 millisecond away from the movement of this system, which is gonna be having the block B moving down, and as a result, block A is moving up. So B is gonna go down and the A is gonna go up the hill or the incline here. So the way we're gonna solve these questions, these types of question, is that we have to draw the free body diagram for each block. Let's start with the top one because it's easier. So we're gonna draw the free body diagram of block A, and let's see what forces we have for block A. So this will be our X, consider this our Y. Let's see what forces we have in here. So we have one single cable that goes around the pulley and attaches to the B. So we have the tension in that cable, which we can call it T. We have the weight of block A, which will be vertical, and that's going to be 20 pounds. We know this angle here would be theta, so this angle right here is also theta. We have the normal force from block B to A, we can call this one N1. And since this block is moving in this direction, the friction has to be in the opposite. So we can consider friction here F1. We have the static coefficient times N1, or the normal force that we have. And yeah, that's pretty much everything for this block. Let's do our equilibrium equations. Sum of all forces in X equals 0. So we're going to have 20 pounds, X component of the 20 pounds, sine of theta minus T plus our friction, which was the coefficient times N1. So coefficient is 0.15 times N1. So we have 0.15 times N1 equals 0. So our team here would be 20 sine of theta plus 15 N1. That's what we can get from X, or sum of all forces in X direction. Let's do sum of all forces in Y. And if we do that, we basically have N1 minus 20 cosine of theta would be our Y component downward equals 0. So our N1 is 20 cosine of theta. So we can put this one in the previous equation in here. So our T would be 20 sine of theta plus 0.15 times 20 cosine of theta, which will be 3 cosine of theta. So that's the, again, I'm just going to put a note in here. So this will be equal to 20 from here, 20 cosine of theta, and the whole thing will be 3 cosine of theta. So now we have one equation. That's pretty much everything that we can get from our block A. Let's move on to the block B. So I'm going to draw the free body diagram of block B. So as I mentioned, this is the direction for block B, or the movement of block B when it's about to move. So if that's the case, the friction has to be in the opposite direction. So we have two frictions, one between the incline and the block. We're going to call this normal force N2, and our F2 would be, have the same coefficient times N2. We also have the friction from the top part, which if we look at block A, we'll see that it's in this direction, which means in here it has to be in the opposite, F1 US times N1, and the normal force is also in the opposite direction of what we have in here based on Newton's law, so it will be downward N1. And we have the weight of the box or the block, which was 30 pounds, and same angle theta in here. So these are pretty much all the forces that we have. Let's start with the Fy. So what we have in Fy is N2 minus N1 minus 30 cosine of theta equals 0. So if we want to find N2, we basically have N1, which is what we found in the previous step, 20 cosine of theta, and all the signs will be positive because we are bringing this part to the right side of the equation. So plus 30 cosine of theta. So our N2 is equal to 50 times cosine of theta. So now we're going to do sum of all forces in x equals 0. One thing that I forgot in here is the tension in the cable. We also have this tension in the free body diagram that I forgot to put. So we have 30 sine of theta minus F1, which was what we found in here, 3 cosine of theta, minus t minus F2. F2 is 0.15 times 50 cosine of theta, so this is mu s times N2, which will be our F2. So we have 4 forces in total in x direction, and we have all of them in here. So our t in here will be 30 sine of theta minus 3 cosine of theta minus 7.5 cosine of theta, or our t is equal to 30 sine of theta minus 10.5 cosine of theta. So we have another equation. We found this one from the block A, and the second equation in here from block 2. If we just subtract 2 by 1 or 1 by 2, really doesn't matter. So we're going to subtract the equation 2 minus 1. So we're going to have 30 sine of theta minus 10.5 cosine of theta equals t. That's the second equation. And this first equation, t is equal to what we found in here, 20 sine of theta plus 3 cosine of theta. So I'm just going to highlight these two. So this one and this one. So if you subtract these two, what we're going to get is on the right side, we have t minus t, which will be 0. So 30 sine of theta minus 10.5 cosine of theta minus 20 sine of theta minus 3 cosine of. So we have these two, 30 sine of theta minus 20, 10 sine of theta, and we have these two minus 10.5 plus 3 minus 13.5 cosine of theta equals 0. Or if we just divide cosine of theta on each side, we have 10 tangent of theta is equal to 13.5. Or our theta would be the tangent inverse of 13.5 over 10. Let's see what we get. And the angle would be 53.47 degrees. And that's going to be the final answer for this question. Hope everything was clear. Let me know if you guys have any questions. And you guys take care. I'll see you in the next one.